Hello everyone, I am Purnendu, a PhD student at the Atlas Institute, University of Colorado, Boulder. I am here to present the work ElectriFlow, Soft Electrohydraulic Building Blocks for Prototyping Shape-Changing Interfaces. This work is done in collaboration with my co-authors Sasha M. Novak, Eric Ekam, Christoph Keplinger, Mirella Allister, Mark D. Gross, Carson Bruns, and Daniel Leithinger. We propose a new prototyping technology for shape-changing interfaces. Electrohydraulic mechanisms are ubiquitous in the biological world. Nature prefers electrohydraulic phenomena to drive shape change. For example, plants like Venus flytrap catch their prey through leaf closure employing electrohydraulic forces. The drastic shape transformation in certain species of octopus is a result of electrohydraulic phenomena. A pufferfish threatens a predator by filling its elastic stomach with fluid, also under electrohydraulic effects. Electrohydraulic processes drive shape change in plants and animals and augment their ability to communicate and interact. In the field of human-computer interaction, taking inspiration from natural world, bio-inspired shape-changing interfaces have been proposed. Traditionally, they are constructed out of soft prototyping techniques, which generally rely on pneumatics, humidity, or heat for actuation. But they also suffer from limitations like being bulky in terms of control system and slow in shape transformation. In this work, we present electrohydraulic actuators as building blocks for prototyping shape-changing interfaces. These compliant actuators generate an immediate hydraulic force on electrostatic activation without an external fluid supply source. They are silent and fast in operation and can be fabricated with commodity materials. Here, we present the general design of these actuators. It consists of oil-filled flexible pouches partially covered with flexible electrodes on both sides, as shown in figure B1. When a DC voltage of the order of 8 kilovolts is applied across the pair of flexible electrodes, they tend to zip together, shown in figure B2. This zipping motion of electrodes displaces the fluid between them to the surrounding volume, resulting in shape change, as shown in figure B3. These pouches are further attached with strain limiting layers to create sharp hinge-like bends. A thin insulating layer between the electrodes and the strain limiting layer is necessary for fluid failure-free operation of the actuators shown in figure A. These actuators can come in a variety of geometries. We propose the design of three such novel actuators: the hinge bending, the crescent, and the quarter moon. Here we show the actuator geometries along with their shape transformations. We also present a design tool to aid the design and fabrication of these actuators. A user can load the predefined actuator geometry and adjust the parameters according to their needs. Afterward, the tool allows the user to visualize the shape change and export fabrication files. These actuators can be fabricated with commodity materials and easily available tools. We begin by heat sealing two pieces of polymer sheet using custom modified head of a CNC machine to generate the outer geometry of the pouch. We leave a small input port for oil filling. Afterward, we manually fill the pouch with silicone oil using syringes and seal the input port. We then paint the flexible electrodes using conductive carbon paint and eventually trim the access polymer sheet. Here we show the DC power supply used to activate these actuators, powered by a lithium polymer battery similar to the ones used in smartphones these days. Though the activation voltage is of the order of kilovolts, this power supply ensures very low current consumption, making these actuators human safe. Here, the bending angle is plotted against the applied voltage for each of the actuator types. A crescent actuator can produce a smooth organic bend with a maximal bending angle of around 60 degrees, while the quarter moon actuator produces sharp bends with a bending angle of around 40 degrees. Butterflies are fascinating organisms given their ability to rapidly actuate their wings. The butterfly wings can actuate at a frequency of around 10 Hz, but for certain species of moths, it can go up to 26.1 Hz. ElectriFlow actuators can act as a great prototyping technology for design of a bio-inspired butterfly soft robot, given their compact design and high frequency of actuation. Here we show an example of prototype of a butterfly composed of two crescent actuators embedded in the wings that can actuate up to a frequency of 25 Hz. The compact design of Crescent actuators ensures they can be embedded on thin film sheets for character animation. Here, each of the ears of the character has an actuator underneath. Crescent actuators can be combined in a wide varieties of numbers and configurations depending upon the need for prototyping. For example, a group of crescent actuators form the basis of a flower that blooms. Flexible displays enable new opportunities for interaction with mobile devices. To explore a thin form factor flexible display, we prototype a shape-changing mockup with the embedded bending quarter moon actuator. The quarter moon actuator ensures a sharp bend for the display without needing a strain limiting layer. We hope in the future, electric flow may act as the basis for actuating such a flexible display. The actuators can bend like a hinge and actuate light as well as heavy objects. For example, here for the hinge bending actuator, the maximum weight lifted without reduction in bending angle was 13 grams. Here we show the two example prototypes as an actuating box and an actuating origami bird. To summarize, we presented ElectriFlow, a novel prototyping technology for shape-changing interfaces. These actuators offer novel features like compact design, rapid actuation, silent operation, and easy fabrication. The compactness, immediate actuation, and silent operation of these mechanisms enrich the library of prototyping technologies for shape-changing interfaces. During the process of developing this work, we also realized a number of limitations that open up possibilities for future work. Like we realized the need for user evaluation of the prototypes. This work primarily focused on prototyping the output of shape-changing interfaces and less on sensing the user input. Adding input sensing modalities such as embedded touch sensing would greatly increase the interactive capabilities. We also think this work opens up possibilities for other new kinds of soft electrohydraulic actuator geometries with novel functions. There is also a possibility of adding a simulation feature in the software tool as well as lowering the voltage of activation by choosing better materials as well as insulating the electrodes. Thank you so much for being here and listening to this work. I will be happy to take questions.